Welcome to the Deep Dive, the shortcut you need to understand the most cutting-edge research driving modern AI. Today, we're cracking open a really critical architectural shift in how large language models handle external knowledge.
We're talking about retrieval-augmented generation, or RA.
Exactly. RGRE is absolutely essential. It's how you keep these models grounded in actual facts and stop them from, making things up.
Right, the hallucinations that were such a huge problem early on. But the thing is, RA itself has a pretty fundamental flaw in its design. Well, you could say it's mathematically broken for deep learning.
And that's this disjoint optimization problem, right? You've got two different systems. One is the retriever, which goes out and finds documents.
And then you have the generator, which reads them and writes the answer. And they pretty much operate in their own separate silos.
Which leads us to the core mathematical problem here, the broken gradient.
That's it. So when the generator makes a mistake and produces a bad answer, it calculates a loss. That's the gradient, the signal that says I failed. But that crucial signal, it can't get back to the retriever.
You can't tell it, hey, you picked the wrong documents for me.
Exactly.
Why not, though? I mean, that seems like the most logical thing. If the answer's wrong, that signal should just flow all the way back, shouldn't it?
It should, but the actual act of retrieval, picking the top 5 or 10 documents from a huge database, that's a hard, discrete choice.
It's a yes or no decision.
It's a step function. You either pick document A or you don't. And calculus, which is what powers all of this training through gradient descent, it needs smooth, continuous functions to work with. A step function like that, its derivative is 0. So when the gradient hits that selection point, it just hits a wall, stops cold.
So you've got this efficiency nightmare from processing tons of raw text, and you have this hard mathematical wall blocking any kind of real holistic training. And that is what our deep dive is all about today. We're looking at CLARa continuous latent reasoning, a new framework from Apple and the University of Edinburgh that proposes a, frankly, really elegant solution.
It's about unifying retrieval and generation in a single shared continuous space,
allowing for joint, differentiable, and just mathematically sound training.
CLARa's whole mission is to basically dissolve that discrete barrier, making sure the retriever and the generator are speaking the exact same mathematical language so those gradients can finally flow smoothly.
Okay, so before we can fix that broken gradient, we have to deal with the first problem, which is just the sheer inefficiency of it all. Standard RGRE systems are just choking on context length.
Oh, absolutely. Every time you feed raw text into these models, computational cost just balloons. It scales quadratically, sometimes even worse depending on the architecture.
It's so redundant.
Totally. You might have a whole Wikipedia article, but you only need one single fact from it. Yet the model has to process thousands and thousands of useless tokens just to find it.
So how does CLARa get around that?
This is phase 1, what they call saline compressor pre-training, or SCP.
SCP, the cleanup crew.
That's a great way to think of it. Its job is to take these long, raw documents and replace them with a set of really rich, highly compressed continuous vectors. They call them memory tokens.
And this distillation process, it's not a small reduction, is it?
No, we're talking about factors of like 16x or even 32x. This is what lays the foundation for that shared continuous space we need for the next step.
But isn't there a risk there? Compression almost always means you lose something. How do you make sure these vectors are still useful and semantically deep instead of just being some shallow summary?
That's the brilliant part. They mitigate that risk with a really clever pre-training strategy. They use a large LLM to generate synthetic structured training data based on Wikipedia, and then they impose 3 specific types of supervision to force the compressor to focus only on the important stuff.
Okay, what are those 3 types?
So first you have simple QA. This is just for retaining those fine-grained atomic facts.
Like, in which plant family is this specific plant classified?
Exactly. The model has to compress the whole document, but still keep that one key fact. Hamamelidaceae. It's pure factual grounding.
Okay, that makes sense. What's number 2?
Second is complex QA, and this is really key. This forces the model to promote relational reasoning, to connect facts that might not be right next to each other in the text.
So it's not just about what the facts are, but how they relate to each other.
Precisely. It's pre-baking potential multi-hop knowledge right into the compressed vector. This is vital because the whole point is latent reasoning, not just simple retrieval.
And the third type was paraphrasing.
Right, paraphrasing. This just ensures linguistic robustness. You can change the surface words of the document all you want, but the core meaning has to stay identical in that compressed vector. It forces the model to ignore fluff and focus only on the essential meaning.
That feels like a really complete system. The QA handles the facts, and paraphrasing handles the efficiency. But let's get back to the math. Because even with all this, if you're just training it on QA tasks, what stops that compressed vector from just drifting off into some unrelated part of the embedding space?
That is where the mathematical control comes in. Specifically, the compression alignment loss, which they call LMSE. It's a mean squared error term that acts like a tether.
Okay, paint me a picture of that tether. How does it work?
So imagine the meaning of the original long document is a specific point in this high-dimensional embedding space. You need your new compressed memory tokens to land right on top of that same point, or at least very close.
And LMSE is what forces that to happen.
Yes. Mathematically, it minimizes the squared difference between two averaged hidden states.
The first average being from the full raw document, and the second is from the new compressed tokens.
Exactly right. They take the hidden states of all the original document tokens and average them. Then they do the same for the handful of new memory tokens. LMSE just minimizes the distance between those two averages.
So you're forcing the raw text and the compressed text to share the same mathematical center of gravity?
That's the perfect analogy. The final loss function for this compressor has a term, lambda times LMSE. And that is a really strict fidelity constraint. Without it, the compressed vectors could just drift away, lose their semantic connection, and become basically useless noise. That mathematical leash is what makes SCP work.
Okay, phase one is done. We now have these dense, efficient, and mathematically aligned compressed documents. The data is ready. But now we're back at the hard problem, the end-to-end training. How do we get the query reasoner and the answer generator to actually talk to each other without hitting that discrete brick wall?
So the goal is joint optimization, right? Using a single objective, which is just the standard next token prediction loss, CLaRa. But first, the query reasoner, θQR, has to learn its new job.
Which is what, exactly?
Its job is to represent the query in the exact same continuous space as those compressed documents we just made. And critically, it has to learn to anticipate what information the generator is going to need. That's a much higher bar than just matching keywords.
So given a question, it's not just encoding the words in the question. It's trying to encode the semantic region where the answer must live based on everything it's learned about those compressed documents.
That's the goal. But we're still stuck with the discrete retrieval step. We have to pick the top cake documents. We still have to get around that mathematical discontinuity.
So how do we cheat calculus?
We use something called the straight-through estimator for the top case selection. This is the mathematical trick at the heart of CLaRa. You can think of it like a special kind of gate that acts hard in one direction, but is like infinitely soft in the other.
Okay, walk me through that gate analogy.
So during the forward pass, when the model is actually running and trying to generate an answer, we need that hard, discrete selection. We have to pick the absolute best Kate documents. That's what they call Z-hard.
And that's the step that creates the problem.
That's the one. But during the backward pass, when we're training and calculating the gradient from the loss, we need a smooth path. So for that, we calculate a smoothed, continuous distribution, Z-soft. It's derived from the similarity scores, usually using something like a softmax function, and it gives every single document a non-zero probability of being relevant.
I see. So the Z-soft distribution basically gives the gradient a smooth hill to climb back up instead of a sheer cliff. The loss signal can touch all the potential documents, not just the ones that made the hard cut.
Precisely. And then you combine them. The final selection uses the hard choice for the operation, but it uses the soft version for the gradient flow. They do this with a function called the stop gradient operator. It basically ensures that the discrete part is there for the forward pass, but the gradient just flows smoothly through that Z-soft path on its way back.
That is incredibly clever. But are there any risks to that? You're using an approximation, a smooth path that wasn't the true path. Does that introduce noise or instability into the training?
That's a really good question and a valid engineering concern. But the theoretical analysis they did suggests the benefit just far outweighs any potential noise. The stop gradient operator actually helps stabilize things by separating the concerns. The hard decision influences the output, while the continuous path only influences the parameter updates.
And that separation allows that final next token prediction loss, CLaRa, to flow all the way back and update both the query reasoner and the generator jointly.
For the first time, yes.
Yeah.
A true end-to-end optimization of the whole pipeline.
So what's the ultimate mathematical payoff here? What do you gain from this differentiable link?
This is the most profound part, I think. The retriever gets what they call dual complementary learning signals. The feedback it receives is just far superior to anything in a traditional RDOT model.
Dual signals, what are they?
Well, the first one is pretty simple. Probabilistic alignment. The gradient rewards the system for ranking the correct documents higher. This is sort of what a supervised reranker would learn to do. But the second signal, this is the breakthrough, is direct representation level feedback. The math shows that the gradient carries a signal, they call it G in the paper, that actively tells the document compressor and the query reasoner how to change their internal representations to specifically make the generator's reasoning task easier.
Hold on, let me unpack that. You're saying the generator, the part that has to do all the hard work of reasoning and writing the answer, is literally telling the retrieval system how to structure its mathematical space to help it out.
Yes.
So retrieval isn't about some abstract concept of relevance anymore. It's about optimizing for the final reasoning step.
Exactly. It forces the retriever and generator to align on a much deeper level. It's not just about facts, it's about creating the optimal semantic space for producing the final complete answer. That deep mathematical alignment is what gives CLaRa its power.
And the practical results of all this, they're pretty stunning, aren't they? CLaRa manages to get superior performance to raw text baselines while at the same time drastically cutting the context length.
Oh yeah, they found the sweet spot was somewhere between 16x and 32x compression. And this isn't a small thing. We're talking massive savings in GPU memory and inference time. You get rid of context overflow and you actually boost the quality. It's the best of both worlds.
And the thing that really sells this whole idea for me is the retrieval performance itself. CLaRa is only using that weak supervision from the final generation loss, but it's beating specialized models.
It's phenomenal. It often surpasses fully supervised rerankers, like BGE reranker, which are models explicitly trained on human-labeled data of what's relevant and what's not.
Give us the hard number that proves it.
Okay, so on the hotpot QA dataset, which is notoriously difficult, it requires multi-hop reasoning across several documents. CLaRa, at just 4x compression, got a recall at 5 of 96.21%.
96%. And the baseline?
The BGE reranker baseline scored 85.93%.
Wow, that's more than a 10% jump.
A 10% jump, purely because the retrieval system was optimized for the downstream reasoning task, not just for static keyword relevance.
That gain right there seems to confirm the whole theory. Optimizing for what's useful for reasoning beats optimizing for what's just similar.
It does.
And this brings me to my personal aha moment from this whole deep dive, the case study they show of the query reasoner's latent ability.
It's a remarkable piece of evidence. It shows the reasoner isn't just grabbing documents, it's performing implicit reasoning steps before the generator even sees anything.
Okay, let's walk through the query they used. It was, how many yards did the nephew of Ivory Lee Brown get during his 2004 true freshman season?
A classic multi-hop question.
Yeah.
The model has to figure out, okay, first, who is the nephew of Ivory Lee Brown? That's Adrian Peterson. Second, where did he play? Oklahoma. And third, what were his 2004 freshman stats?
So when they actually look inside the query reasoner to see what semantic topics it was focusing on, the decoded tokens included NFL and Oklahoma.
Words that were nowhere in the original question. It's truly amazing.
It means the query reasoner had already done the latent reasoning. It made the connection to the NFL player, it identified the University Oklahoma, and then it optimized the query vector to go find documents about Adrian Peterson's stats, not just stuff about Ivory Lee Brown's family.
It mathematically engineered the retrieval to enable the reasoning path that it knew the generator would need. The continuous latent reasoning from the name CLaRa, you can see it happening right there.
It's not just looking up keywords, it's predicting the shape of the answer.
And directing traffic accordingly.
So CLaRa feels like it's much more than just another tweak to RGRAG. It's establishing a totally new, unified paradigm where knowledge compression and retrieval generation are all linked through this one continuous mathematical space.
It solves the efficiency problem and the broken gradient problem at the same time.
And while the results are fantastic, the paper is good about acknowledging the limitations.
Right. The compressor was trained primarily on Wikipedia. If you wanted to apply this to something like, say, code generation, you would almost certainly need to do some domain-adaptive pre-training to get the same level of quality.
And they were working with medium-scale models, right? Mistral 7B, 5.4B. The really big question is what happens at scale.
Exactly. Is there a model size threshold? A point where a massive model's raw processing power might just overcome the benefits of these compressed vectors. Or maybe the opposite is true. Maybe beyond a certain size, compressed representations always win. We just don't know yet.
Which raises a really fascinating final thought for you to take away. If these continuous compressed representations are this effective at distilling raw documents for complex reasoning, could this type of latent, dense representation fundamentally replace large amounts of raw text storage and processing in future AI systems?
A shift from simply storing information to storing the potential for reasoning.
Could knowledge access become truly instantaneous, with an AI's memory optimized not for storage but for meaning and reasoning enablement? A deep thought to leave you with. That's it for this deep dive. We'll see you next time.